everyone to this morning session. It's a big pleasure to announce the extended talk by Gilles Francfort, who will speak about stability in solids with defects.
Well, thank you very much. I want to thank the organizers, Teresa, Ricardo, I don't know where he is, and Manuel, for the kind invitation. So apparently I'm being recorded. Why they chose me is as mysterious as the role of stability in solids with defects. Maybe it's because of my shorts or something like that. Also, don't be scared or mystified if I shout obscenities during the talk. I was expressly advised to do that so that it would improve the rating on YouTube. You know? So, okay. So this is meant to be a more general overview or targeted to a more general mathematical audience. I think the idea is not so much that the people here are part of a general mathematical audience, but maybe that if it goes on YouTube or something like that, you will get viewed by people who are not experts in this field. So I'm going to try my best, and you'll probably be very bored. But in any case, so that's the title. And as you know, there's a solids and solid behavior can be handicapped or can exhibit a variety of can misbehave in different ways, and so you can have various things happening. For example, you see cracks growing in a glass plate. You could have micro cracks or micro voids being created in concrete. You could have the phenomenon of necking in a steel bar, which eventually will lead to its failure. The bar will break into two pieces. And so these are all defects that modify the behavior of those solids. And I'm going to try to address all of those. What I'm not going to address because I don't understand it, and I contend that we collectively do not understand this, is the interaction is what happens when you try to understand how kinetic energy can interact with the onset and growth of defects. And so I'm not going to talk about this. And what also I think is poorly understood is the finite deformation setting. Although there are mathematical works that deal with finite deformation and the interaction between finite deformation and defect growth, I'm not sure that they're relevant to what actually is happening. One example where we are really far from understanding what's happening is what happens with elastomers like rubber. So when you look at a piece of rubber, you see the things that are called sometimes cavities. There's a theory called cavitation, and it's not quite clear what those are and where they come from. So I'm not going to talk about, I'm going to be in a small deformation setting, and I'm not going to consider kinetic energy. What seems to characterize the evolution, the growth of those defects, be it cracks or this kind of phenomenon which is due to slip lines or to slip lines in metals or those micro voids in a material like concrete, are what seems to characterize their evolution is rate independent. That is the idea that it doesn't matter, that the speed at which you load your sample is irrelevant. And so this is typically not viscosity. So this is the opposite of viscosity, where the rate at which you load your sample or you apply your forces is completely fundamental. Okay, so the outline of my talk is as follows. First, I'm going to spend quite a lot of time discussing a very stupid 1D model. And I'm going to build slowly on it to show you how we end up with the kind of equations or the kind of modeling that we end up with. And then I'm going to, and then this is going to force me to introduce some kind of notion of stability, and then I'm going to investigate the pertinence, the relevance of this notion of stability when, how it fares in various settings, going from one place where actually you really don't need it, which is plasticity, one place where it has mixed results, or its impact is mixed, which is brittle fracture, and one setting where it fails, in my opinion, miserably, which is brutal damage. And I hope I get there. So, as I said before, the overarching assumption is quasi-static. It'll be also either thermal in the sense that I'm not going to worry about temperature and how it couples to the mechanical behavior. This would only complexify the issue, but I don't think it's essential. Although it might be very important from an application standpoint. So, since it is, after all, an overview, I cannot assume that you all know anything about continuum mechanics, so I'm going to have a crash course in solid mechanics in one page. Okay. So let's say, but it'll be all that I need really for my 1D model. So let's say you have a bar of length L, which is built into a wall at one end and free at the other end. And then you, let's say you pull on it with a force, or you impose a displacement at the right end of the bar. And so I call it a stretch, and you displace the end. So each point of the bar will displace by some value, u of x, and will experience some force. So really it's not the point that is subject to a force. It is either, so if I have a point here, it's either the left part of the bar or the right part of the bar. But let's say, I say that point will experience some force per unit length, which I will call the stress. And of course, not all points can move the same way, because on the left-hand side, this point is fixed, and here it moves. So U will be, so the stretch will depend on the point. And some parts of the bar will stretch more than others, and so the stretch of a section of length delta x will be measured by this. So locally, the measure of the stretch would be the derivative du dx, which I will call epsilon, the strain. And of course, you have equilibrium in the absence of kinetic energy. Each section of the bar must be equilibrated, which yields, if you take a section of length delta x, d sigma dx equals 0 by going to the limit in delta x. So you have two equations. I mean, it's a very simple equation, but you essentially have two equations, and you have one unknown. Two unknowns and one equation. And so you need an additional relation, And this is what the constitutive law is, or the constitutive equation. And the simplest one is linear, and it's called linear elasticity. And it's a linear relation between stress and stretch. E, the coefficient in this linear relation is the Young's modulus, and it is assumed to be positive because the greater the force that you apply, the larger the stretch should be, which kind of makes sense. You can view this as some relation which derives from an energy, the energy being here some quadratic energy in the string. This is a string here. So if you postulate that the elastic energy is 1/2 of E epsilon squared, you get that sigma is the derivative of E with respect to epsilon. That's all you need to know about mechanics. And then, let's go to the 1D model. So I want to, so with respect to the previous slide, what I want to do is to introduce a variable which I will call D, which has a property that the Young's modulus here is a function of D, which I will call the damage variable, and since I want to essentially talk about damage, I want to say that if D increases, then the properties of the materials are deteriorate, which means that E should be a decreasing function of D. So that's my assumption. I'm not saying D should increase, but if it increases, then E of D decreases. So now we have the same equilibrium equation, d sigma dx equals 0. We have an elastic energy density, which is the same as before, except that E is a function of D. And then we have the boundary conditions, which at x equals 0 are that U should be 0, and at x equals L could be a displacement boundary condition. So I apply a displacement, which is a function of T, or a traction boundary condition. I apply a force, which is a function of T. So first case is often called in the mechanics literature a hard device. This is called a soft device. So now I have one more unknown, D, same number of equations. Clearly, I'm missing something. So what am I missing? So let's say that it's up to you. How do you want to model this? But something which makes sense and which is very classical is to say I have a threshold. So let's say that I say that the force in absolute value should be less than some function of D, and as long as it is strictly less than that function of D, whatever the damage state was, it'll remain at that state. So this is kind of the simplest way that you can envision how damage, I call it damage, D, let's call it D. D will evolve with time. It seems like a natural way. Of course, you can come up with whatever you want, okay? But that seems to be fairly natural. So is that enough? So if I say that, do I have enough together with that equation, the elastic energy density, which really tells you what sigma is as a function of epsilon, is that enough to determine the evolution of this system in, let's say, U and D? And the answer is no, it's not enough. You need something else. So simply imposing a threshold and saying that the damage variable does not evolve if you're not at the threshold is not enough to determine the evolution. So here, you need more. And So you can one. So here you have a choice. What most people in this room do or would do is they would call upon the second law of thermodynamics, what's called Clausius-Duhem inequality, and then they would probably add to it something which comes from the theory of generalized standard materials, and try to write something. So some people call it the bio, whatever. If you're German, you're bio. If you're French, it'll be Clausius-Duhem and generalized standard materials. If you're American, you don't like this. So you would do something like that. So this is kind of the Western way. The Eastern way, which has been, which is less popular, which is probably exactly, which doesn't refer to thermodynamics, does not refer to second law, to entropy, to anything like that, is to use what some people call Ilyushin's principle, other people call it Drucker's principle. I don't want to be very precise here, which is simply that when you perform a strain cycle, the work during that strain cycle should be non-negative. Same result at the end. No, here, purely a mechanical postulate, there, thermodynamics and so on. It yields the same thing. I'm not going to derive it for you, it would be too complicated, but essentially what it says is the following. On top of this, because of either this principle or that principle, you get the following things. So I assume E is a smooth function of D, that the derivative minus the derivative with respect to D of the elastic energy is less than some constant, which is not the same as that one, but very important, which is independent of it. Second, that D dot will be 0 unless you have equality here. And third, that D dot will be non-negative. So this delivers the fact that damage can only increase, and then it tells you how it increases. So if I sum up what we get the following. We have the equilibrium equation. We have U0 equals U of Z0 equals 0. The boundary condition at x equals L, as I said, it could be a displacement boundary condition, hard device, or a traction boundary condition, soft device. The fact that D increases, this condition, okay, and that condition. Okay. So for those of you who are used to gradient flows, this is completely different. It doesn't have a gradient flow structure, and I contend that gradient flows are essentially equivalent to introduce viscous dissipation. So when people write a gradient flow, I mean, it could be more complicated because it depends on your topology, but essentially what you're doing is introducing viscosity. Here there's no viscosity. And I'm going to try to keep it that way, in contrast to maybe what a lot of people talked about yesterday. So now you have those equations, and now it's a math problem. How do you solve this? If you're a PDE person and you try to go ahead and solve a problem like this, you get stuck. You get nowhere, even in a 1D problem. So you have to somehow massage this system, and what emerged throughout the 90s is that the right quantity to look at is something which mixes together pears and apples, which is to add to the elastic energy this thing, KD. And then this system is completely formally, this is completely formal, equivalent to a variational inequality, which is the following one. It tells you that, so I wrote it like this. So let's take a little bit of time. So W is a function of epsilon and D. I replace epsilon by du dx, D is D, and then I do variations both in V and in D, which is why you have a dW over d epsilon here, a dW over dd here, and then this term here is in red because it only comes into play if you're doing a traction at the right-hand side of the bar. And now, what are the V's that you can take as test functions? Well, those are kinematically admissible V's. So that's a word to say that in the case where you have a force, V is not constrained. In the case where you have a displacement at that end, then V should be 0 at that end. And as far as D prime is the test in damage, the damage test functions, if you want. D prime should be non-negative, and this is kind of what's left of the constraint that that D should increase with time. So this is this variational inequality that you get, and on top of it, you get energy conservation. Not formally, it's energy conservation. There's no missing energy, nothing. And I insist on this because it seems to be lost in what people have been doing. Exact energy conservation. So you get that the derivative in time of the total energy. If I call this the energy, the total energy, maybe minus the work of the external forces, if you have a force, is equal to some kind of work of the, so this would be akin to a first principle in energy conservation. But when you look at books on energy conservation in mechanics, usually they don't deal with boundary conditions. So that, and they don't include this term in the time derivative, which is why it looks a bit different, but this is just an energy conservation type statement. So now let's say, now if you're a mathematician, you say, what can I do with this? And clearly, the main problem is this variational inequality, because what do you do with that? So what you do is you introduce this kind of potential, if you want, which is a function of t and of the test fields v and v prime, which is given by this energy minus the work of the force, and this should be a v, not a v. For any v which is kinematically admissible, and for any d prime which is greater than d of t. And the variational inequality is just a first order necessary condition for, let's say, something that could be called local minimality. So it just says that the derivative of p applied to any test, admissible test field, should be non-negative. Once again, it's not 0 because of the constraint that d should increase. So it's unilateral. If you didn't have that constraint, you'd get 0, and then you get for every d prime. So now you have this. Now we are remarkably ill-equipped to deal with this kind of inequality, except in one case, when W of epsilon and D which comes into play here, is a convex function in both variables. If it is a convex function in both variables, then this condition is just equivalent to global minimality. So it tells you that u of t, d of t is a global minimizer of p of t, and those are the two free entries over all kinematically admissible fields, or unmissable fields. So all these and all d prime greater than dt. And this is exactly what will happen in plasticity. In plasticity, you will have two variables, and this function, the energy, will be a convex function. And so writing the variational inequality is equivalent to writing global minimality. In this context, what does it mean to be convex? It means this. Trust me, it means that. And this means that 1 over E of D is concave. So if 1 over E of D is concave, which is not the same as E of D convex, then you're convex, and then everything is fine and dandy. What happens if it's not? So let's take the opposite of this, but let's not play with the fact that it could be 0. Let's say that this quantity here is greater than alpha, strictly greater than 0, I should say. Then you're in trouble, and you're in trouble for several reasons. If you're dealing with the bar with traction, so a G, at the right-hand side. Then you can prove that you cannot have existence of actually for the original, you don't need to recast it in this framework. For the original system, you will not have a solution as soon as G is strictly greater than this quantity. So your problem is meaningless. What you wrote is meaningless. Another issue is uniqueness. And for example, if you take the displacement problem, so you apply a displacement at x equals L, then you get, if the bar is long enough, you will get many solutions. So you could have non-existence, or you could have multiplicity of solutions. So we need something else. So first, if you have non-existence, you have non-existence. It's not by having something that you will cure non-existence, but in the case of multiplicity of solutions, could a notion of stability help? And the natural notion is the one that everybody in the talks yesterday was playing with, more or less, which is the idea of local minimality. So saying, well, this looks like a first-order necessary condition for local minimality of the state u of t, d of t. So maybe local minimality would be good. So now, of course, the devil is in the details, and you have to know what does it mean, a neighborhood of the solution. So local minimality immediately beg the question, what do you mean by local? It doesn't matter. So local minimality. Well, no matter what local minimality you take, localization, in this case, in the case where you're in trouble, localization always occurs once the damage stops. That means that once D ceases to be 0, or essentially immediately D localizes in a small neighborhood and starts growing and growing to infinity. So there's no, so this notion, so you'll have some kind of instability, And that means that, this is a band model if the damage is not bounded from above. So if you insist on this model, you need at least to bound the damage from above to prevent it from creeping up to plus infinity, which you will in this situation immediately, in spite of a notion of stability. Okay. So let's now quickly review how this fares against actual models, real models. So the first one is plasticity, and that's a good case because so this is small strain elastoplasticity. So in a nutshell, you have to replace the UDX because you're in a higher dimension by the linear strain, which is a matrix, because U is a vector from omega, which is some bounded set in R3 to R3. Grad U is a matrix, and what measures the elongation, if you want, is this quantity that's the right measure of the geometry, if you want. And so this is a symmetric matrix, but epsilon of U is not. So what's happening is that epsilon of U is a sum of two terms. One term, which is the elastic part of the strain, and one term P, which is a plastic part of the strain. And the plastic part of the strain is only deviatoric in the sense that its trace is zero. This is because it is commonly assumed that plasticity does not occur in the Vogue, only when you have shear type deformations. So you have this condition, then you have a threshold that tells you that the deviatoric, while only deviatoric means you remove the trace part of the tensor or the matrix. So this is exactly the same law as before, sigma equal E epsilon, except that now it's not epsilon, it's just the elastic part of the strain, so it's epsilon U minus P, and A now is not a number, it's you have four indices, it's an elasticity tensor. You have what was d sigma dx equals 0 because divergence sigma equals 0, and because P is deviatoric, you only put a constraint on the deviatoric part of the stress, and all that I wrote before amounts to this kind of relation here. So this condition that minus 1/2 of T prime D epsilon was less than K. I'm not asking you I'm asking you to trust me that that's what it comes down to in this context, to this condition, which for people who are used to convex analysis is a subdifferential type condition, okay? And you have let's say on the boundary of your domain, you have a displacement boundary condition everywhere, which is W of T, which you assume to be smooth enough. So as before, you introduce this kind of potential energy. This is the elastic energy, and this time it's not linear anymore, it's absolute value of Q minus P of T. And it's a convex function of V and Q, so the problem is formally equivalent to a global minimization problem. U of T, P of T minimizes this energy over all admissible fields, plus conservation of energy, which in this case looks like this. Or I could have put this inside, except I would have to put the total what's called the total dissipation by most people, which is integral from 0 to T of that. So global, as I said, global stability is the only kind of stability, and for more mathematically inclined people, you do have a solution for this evolution equation. This solution is in a space which allows, in U, in a space BD, space of bounded deformation, which is the equivalent in this setting of BV, the space of functions of bounded variations. So in a way, there's some kind of relaxation in the sense that you cannot expect the solution to be smooth in space. And of course, you have to rewrite everything appropriately. The boundary condition can be relaxed, and the reason is that, so essentially, all the trouble comes from the fact that you have linear growth here of this term. So when you look for minimizing sequences which are bounded in L1, you end up with measures. So you expect the plastic strength to be a measure, and it's a measure that can creep up to the boundary. And if it creeps up to the boundary, then it can destroy the boundary condition. So it can prevent the boundary condition from being attained. So you have to be careful. There's a relaxation of the boundary condition. But these are mathematical details that I don't want to get into. The important thing is that you do have pretty much existence here, so it seems like the model is good. Why it's not that good? Because uniqueness is bad. Now, here it's a bit subtle. So in plasticity, you can show easily that the stress is unique, but not U of t. So let me be more precise. It was not now known whether U of t was unique or not. Now, as far as I know, there are only 2 examples of uniqueness or non-uniqueness in a 3D setting for plasticity. And here I'm showing you very quickly one example where you can have uniqueness or non-uniqueness depending on really the fine details of your problem. So this is called the Biaxial Test, and it's essentially a block, or not a cube, because it has height L, it has the direction over there is L, and this, is H, and this direction is L. So it's a square here, but in that direction is H, and H is strictly less than L. Okay. And then what you do is you let it here, there's no friction, it can move if you want, and on the 2 opposite sides, you don't apply anything. And on those sides here, you apply a force, sigma bar 2. These are the elastic constant. And then here, on top, you apply an increasing displacement with time, TL. And then you can prove that you have a spatially homogeneous solution, and that it is unique except for a very specific value of this traction. And in that case, not only is it not unique, it's pathologically non-unique. It's non-unique in the same way that the Gilles-Francfort solutions for Euler are non-unique. That is, you can create pretty much everything you want, and including things that are extremely ugly, for example, Cantor-type functions. This is, to my knowledge, the only example of non-uniqueness in 3D. There was an example earlier by Gagnan of non-uniqueness in 1D, but not in 3D. I see time is flying, so let me go to brittle fracture. I don't know if I'll get to damage, but it doesn't matter. So brittle fracture is bad, so it's bad. So let's say you have a domain, and on the domain you have a crack that can move along a preset path, and let's say that the crack is connected. So once you know the crack length, you know the crack, gamma L. And so what you have is you have, and let's say you apply this kind of boundary condition on the boundary, and let's do the simplest setting, which is called anti-plane shear, where it's a 2D domain and the displacement is orthogonal to the domain. So you have U is a scalar. You have, so sigma, the stress is now a vector, if you want, and you have a relation like this on the uncracked part of the body. You introduce, exactly as before, this potential energy, but first, so first you solve the elasticity problem away from the crack, or on the uncracked part of the body, with natural boundary conditions here, and then you, so this is what this computation is, and then you add this KL, which is what according to Griffith's theory, Griffith was the founding father of fracture mechanics, the kind of energies that would be associated with a crack of length L. And then you just turn the cranks, and so the conditions that I had written before, here in this specific context or setting, specialized to an inequality like this, and the fact that if L dot has to be zero unless this is zero. So this is related to what people call the energy release rate. So then all depends. You only have one variable because I've kind of what do you call it? Gotten rid of the dependency V by first performing this minimization in P. So the discussion is around whether L is P is a convex function of L. And here you could put T or 1, essentially P of T and L is T squared P of 1 and L. Not quite, but essentially it is. So all you need to talk about is P at 1 and L. And if it's a convex function here, then no problem. You have convexity, you're back in the nice, you do global minimality, nothing ever happens. Now, if P of 1 and L has convex and concave part, you should expect instabilities in the concave parts, exactly as I described in the 1D damage problem. So you could introduce stability, you can introduce global stability, which would be a good stability criterion, and then I'll talk about this, or local stability. But no matter what you introduce, global or local, you get instability for forced loads. So as of August 2018, nobody knows what to do in the case of force. Essentially, because of rigid body displacement, you can cut off, let's say your force applies only on part of your body, you cut off that part, and because of this linear term, you send it to minus infinity, your energy goes to minus infinity, you're done. Right? So you can do all the local stability analysis you want, it won't help. Nobody knows how to handle this in this model, period. We have no idea, no clue. I find it rather pathetic, actually. So what about if you have displacement type boundary condition? Then global minimality is good, and at least in this room, everybody knows about this. You get a solution. You have to use the technology introduced by the Georgi for image annotation, and you get a solution in the space of special functions of boundary variation. You get a crack which increases with time, so there's no problem with existence. Uniqueness is impossible, but okay. Now we mark that with global minimality and a displacement boundary condition, you always have initiation. But if you start with a domain where you have no cracks, you will always initiate a crack, because if you have no cracks, then the elastic energy being quadratic, let's say linear elasticity, then if your displacement grows like t, your boundary displacement grows like time, then your energy will grow like time squared. And at some point, you're better off coming with a pair of scissors and cutting away the boundary. You pay something which is proportional to the area of the boundary, but it will be better from a global minimality standpoint than having t squared. So you always get initiation. Whether it's the right initiation or not is another issue. What about local minimality? Independently of the resulting global minimality, nobody knows how to do existence for local minimality. What about initiation? It's, and that's a theorem, is generically impossible to initiate a crack from a situation when you're uncracked. So if you have what's called a weak singularity, which is what happens in the typical setting of fracture mechanics where you have what's called a notch, and you expect the crack to start with the tip of the notch, then you can prove, this is what's being said here in mathematical terms, that the elastic solution is always stable. By the way, I'm not quoting anybody during this talk. That doesn't mean that all the results are mine or those of my collaborators. I have a complete list, or not complete, list of people on the last slide. So, for example, this result is by two fellows in the room, Giacomini and Ponziglioni, as well as Chandler. So now, the advantage of global stability is that it is relevant to approximation by gamma convergence. So now the Italians are happy, you have gamma convergence. And this was the work which was starting with the work of Ambrosio Tortorelli, which was mentioned quite abundantly yesterday, especially during Matteo's talk, Matteo Negri's talk. So you can do an approximation with a phase field. So this is, I won't specify in which sense this is an approximation, but essentially you replace a crack by some kind of process zone with a variable z, which is let's say between 0 and 1, and the details here don't matter really, which will essentially concentrate to be 1 or 0 where the crack is. So that's what is written here. The crack is essentially the place where the epsilon z of x equals 0. So from a global stability standpoint, this is a good approximation, except that now, if you want to do computations, so you do a time discretization, and at each time you want to minimize this, which would be a gamma approximation of your real energy. Unfortunately, this is not convex it's convex in V, it's convex in Z, but it's not convex in the pair. So from a numerical standpoint, an algorithmic standpoint, you don't know how to do this, perform this minimization. Matteo yesterday showed us a very sophisticated way of doing what could amount to some kind of minimization leading to I want to say boundary variation, but no, it's not that. A BV solution in the sense of Riccardo Rossi. But if you just do alternate minimization, we don't know what we're doing, but it seems to work. Okay? So these are, for example, so this is a snapshot of the computation of a glass plate being dipped. So I don't want to get into the details. This is an experiment. This is a computation. And I'll show you, so this looks good, but it's only qualitative, but I'll show you here now. This is a glass plate which is brought down onto a bed of ice. It's at 20 degrees, and the bed of ice is at 0 Celsius. And this is what you observe. So you observe cracks. There's a lot to say of this, but essentially this is what you observe. And this is what is being observed
qualitatively, but it goes further. If you look at the heights, the distance between the cracks and so on, between the experiment and the computations, there's very, very good agreement. Who knows why? Okay? But there is very, very good agreement. I could argue why, but it would be a different talk. So for some reason, this alternate minimization technique seems to capture exactly what you want, with a caveat about initiation in some setting. So just for fun, same experiment, but in 3D. You take a plate and you put it on a bed of ice, but this time it's a 3D plate. Okay? And what I'm going to show you is a crack as it moves up. And this is a computation, a very heavy computation by Gilles Francfort. So I'll show you how the crack moves as time goes. So first there are no cracks, and then you have initiation, and the crack moves, and there's a coarsening process, and this is a crack. Oops. This is, so let me do it again. And you see this coarsening of the crack, and those things are the cracks on the surface. And this is at least qualitatively what you observe. For example, if some of you have been to Potosi or to the what is it called now? In Bolivia, Uyuni, then you see those kind of things on the surface of the dry lake. All right. What about the ugly? I have 2 minutes for the ugly. 10 minutes? Oh. So let's talk about the ugly. So the ugly is damage. Our version of damage. It's not always so damage. So we saw before that in the 1D case, there was no hope to get any meaningful model for damage if you didn't bound the damage from above. So here we're going to be very simplistic. We're going to say you have two states, a healthy state and a damaged state. And so you will have a weak material, the damaged material, and a strong material, the undamaged material. And in terms of stress-strain relation, they're characterized by a different slope. So this is the equivalent of E, the Young's modulus, for the strong and for the weak. So at some point you will be damaged, at other points you will not be damaged. So you can introduce a characteristic function of the damaged material, and the fact that damage increases means the characteristic function increases with time. We're going to assume that there's no damage to start with. The stress will depend on whether you're in the undamaged area or the damaged area. You'll have divergent sigma, and then we write exactly the same condition as before. So these are the conditions in this case. And so that's exactly what I wrote before. So essentially, you as long as you're not damaged, you need this. This quantity should be below K, and you get damaged if you were not damaged before, and you reach K. I mean, no. If you get damaged at some time, it means you were not damaged before. And it's the first time at which you are damaged. It's because you had this condition. Or it's not, what I'm saying is not clear, but I think you understood. So you introduce the same energy as before, the elastic energy, plus the energy associated with damage. And you do the same thing as before. And so let's say you want to do global minimality, which is a natural thing. Well, then you would, the first thing you should try, then you would like to minimize this among all possible u and v and chi. And so you can get rid, because chi is only 0 or 1, you can easily get rid of this infimum in chi. So that means that you really down to a one-field minimization problem. You do exactly the opposite as that you did in fracture. In fracture, we got rid of the displacement field. Here we get rid of the damage field, and we're left with the displacement field. And you have to minimize its energy, which is like this. So it's non-convex, and I won't tell anything surprising to anybody here when I will say that because it's non-convex, you expect relaxation. So you got to get relaxation, and so you need to compute, you need to relax the energy. The key word is quasi-convexification, and the Q. And when you compute the quasi-convexification of this energy, which is a relaxed energy, which then that amounts in this particular setting to minimizing to essentially a double minimization. You minimize over all volume. You essentially, what you do is you mix together at a fine scale the weak and the strong material. You get an effective material, which I call A0. And then you look at all the A0 you can get by mixing together in a periodic way, let's say, the weak and the strong material, all the energies that you get. You take the minimum of those energy for a fixed volume fraction, say that. You take the minimum of this energy, then you add k theta, and you minimize in the volume fraction. And that gives you the quasi-convexification, which will look something like this, in this case. So you won't be convex. Okay? So you have some relaxation process. So you started with two materials, and you end up with a kind of mess. It's not clear what variables you should take at the next time step. So at the next time step, you should say, well, what do you do in the next time step? Because already at the initial time, your original problem has no solution. So at the next time step, you could say, well, I'm going to increase the amount of damaged material. But that's bad, because that is completely flying in the face of the monotonicity constraint and damage. Because imagine that you're at step 0, in order to achieve the optimal microstructure, if you want, you had to mix together the materials like this. But imagine that at the next step, for more volume fraction of damaged material, you have to mix things like that. Then you have no monotonicity of the damaged part of the body, if you can think of that. And so this is not the right thing. One possibility is to add to what's already homogenized at the first time step more weak material, and to tailor the dissipation accordingly. You can do that. If you do that and you work, you get, in the end, some kind of evolution, which accounts for monotonicity in this kind of relaxed way, in the sense that at each time you're adding weak material or damaged material to the effective materials that was kind of the relaxed solution at the previous time. And you can do that, you get a very, so I stated the precise mathematical theorem here, but who cares? But, okay, so you've done that, you've gotten an evolution with a solution. So what? What does it have to do with the original problem? Is this a good notion of relaxed evolution? What even is a good notion of relaxed evolution? Well, I don't know. I think it's not. And because he introduces kind of time continuous hierarchy of solutions. It's ridiculous from a practical standpoint. And there are arguments that you could say that the evolution that you get is way too high. It's not the right relaxation. I don't know even how to define it. I know there are some people here that will disagree with me, but I don't know how to define the relaxed evolution. And further, what's interesting about this model is that you can show that you have no locally stable evolutions. So global stability is the only game to play. So forget about local stability and so on, it's completely irrelevant. So, sum it up. It seems like some notion of stability is necessary for well-posedness of the evolution. Clearly, it's necessary, but not sufficient, because we saw that in some cases, even without a notion of stability, we do not have a solution. Further, stability is not something, though that's more, I don't think that's an issue for the mathematical crowd, but it would be an issue for the people in mechanics. People in mechanics think of stability as something which is local. Clearly, stability is structural. So you need a structural notion of stability, so something which depends on the details of your geometry, of your structure, not something which is just a pointwise notion. Okay. Metastability or local stability is too difficult, and in any case, it doesn't seem to cure the things. It doesn't seem to cure instabilities. So is it that maybe kinetic energy will cure something? Yeah, but how do we incorporate kinetic energy? Except in the setting of plasticity, where it's fairly reasonable, in the setting of fractional damage. And how does this affect this notion of stability? So all this, I guess the message I wanted to convey is that we are really confronted by really hard mathematical issues, but our main issue is modeling. And you have to take the modeling extremely seriously, because you can play all the mathematical games you want. It's not clear that they're relevant, and they may end up being completely ridiculous models from a practical standpoint. And we are essentially confronted with a mystery. For example, why is it that alternate minimization seems to deliver on a phase field model which finds its root and its essence in a global minimality argument through gamma convergence, seem to picture accurately, and not only in the example I showed you in fracture, but in many, many examples, seems to give you a complete qualitative agreement with experiments when we have no idea of what it does. Okay. So this is what I think, if you take something away from this lecture, that's what you should take away from it. Thank you for your attention.